Hello everyone, welcome to our class. Today we will start to talk about our Linux systems. So today will be an introduction to your Linux systems, how your Linux systems to manage your source code, and how we use some resource in our operating systems to make our program more strong, more powerful. This is today's topic. So let's see this picture. So this picture shows how your Linux operating system works. Actually, there's a very central unit in these operating systems, which is kernel. You can imagine that the kernel is like the god of your computer. It controls everything. If you want to see the keyboard, the guard is hold the keyboard. If you want to use a network, the kernel is hold the network. So actually, as user process, user program, you cannot easily to use this resource management. Okay, so you can imagine that this is your instance of your program. You try to run data out, and you create the program. You try to do a lot of stuff, printf, scanf, this stuff, and how to do it. Actually, they need to try to send a message to the kernel, and kernel do this for this user process. So actually, kernel control everything. They try to manage everything for user process. User process cannot easily do the stuff they want to do. For example, use a network. For example, actually like try to print message. It's actually this stuff are controlled by the kernel, not the user process. But why we can still use the printf, scanf? Why we can still connect to the network? So because there's some way we can use to communicate with kernel to ask kernel to do us the favor. Do me a favor, kernel, please help me to do it. So this is the concept, and we will talk about this later. The kernel uses three abstraction to compact, to package this resource and use it to manage the resource. The three level of the abstraction is process, the process, and virtual memory and files. These three level of abstraction give the kernel an easy way to manage this resource. Okay, so that's the three fundamentals abstractions inside this kernel design. So let's see the first abstraction, the process. What's a process? Okay, so actually you can imagine that you have ada out, you have a main.c, and you compile it. It becomes ada out. When you run the ada out, inside your program is actually just like, okay, I create a process. So I try to package the information for your program into a process. Okay, so this is the idea. When you run a program, actually the kernel manage this program, this instance of the program run into a process and try to control it. So you can see the kernel try to control each process running in the operating system. So the program itself, the running program, user program made by you, it won't do, for example, stop, or it won't be like, failed because of you cannot get the resource of your screen or your keyboard. It can run, fine because the kernel help it to manage this. And how kernel manage each process, each program? There's so many program runs in your computer. You probably like open Microsoft Word and you watch your YouTube together. So they are software, right? They are different programs, but your operating system don't get conflict between this program. For example, when you watch your YouTube, then your Word file will be destroyed. No, right? So actually, your kernel package, the Linux kernel package, each this program run into a process, and it's provide very like specific information for each process for the kernel to like manage it. So this is the first like abstractions or inside your kernel, inside your Linux kernel. And how the code actually runs. Actually, this is the source code here. So when we have this source code, we try to compile it and we run on the kernel. And the kernel use scheduler. So that's a couple different process. So we only have one kernel. If we only have one kernel, one CPU, and how we run different programs in the same time at the same time. Can we do it? We only have one brain. How can I think about different things, like two things together? You cannot do it, right? So actually, it's not. It's more based on this schedule. Okay, so there's a scheduler inside the kernel to help a kernel to make decision which program I need to run first. So in this case, the kernel will run a process A, the first program, for a while, then it's changed to the process B, to run process B a little bit. Then it's go back to run process A a little bit. So you can see it's not just happen at the same time. It's not. It's more like, okay, you move so fast. I just run the first one, then run the second one, run the first one, run the second one. And every switch is less than probably a milliseconds. So the user won't see it. When you run your program, you just see the result. Very, very quick, very quick, shows everything, right? Because you did not aware of it, there's a switch, stop your program, run another program, then go back to run your program, continue. Because they are happen so quick, and user won't see the delay. Okay, so this is kind of the idea of how your kernel run different multiple process at the same time, and this is called multitasking. Multitasking. So our Linux kernel is a multitasking operating system. Our Linux kernel has two very, very strong function. First one is dominate everything. It's kind of a guard. It's try to manage everything. The second is multitasking. It try to run the program, try to make it do it at the same time, but actually it's not the same because you use the scheduler to switch between these two programs, even more programs. They are based on this schedule. This is the idea. That's the second abstraction. The second abstraction is virtual memory. So for virtual memory, why we need virtual memory? Imagine that right now we have a lot of program here. Each program, they are independent to each other. So they don't know each other. Why? Because kernel is the guard, try to control everything. So they should not to communicate each other. For example, okay, this process one say I use the memory, I use memory address, memory, 1 to 1 gigabyte, and this one say okay, I use the 1 gigabyte plus 1 to 2 gigabytes, and so on. They cannot synchronize this, right? Because they don't have any information about other process. The process itself is self-contained. It's contain a running program and the status. It cannot to include. It cannot to get the message from other process to know how many memory they use. So in this case, how your kernel manage it? So one possibility, you can just equally divide your memory, right? So if I have 4 gigabytes, I have 5 process. I just give each one roughly 800 megabytes. I can try this, but this is definitely not a good idea. Why? Because if you do this, you need to guarantee there's no other process will come. So actually this is not work, because if you assign your resource to this process, which means when other process join, you cannot manage it well. And also, if you are a programmer, it's really hard to estimate. I try to write my code, and I probably need to use the 4 gigabytes or 2 gigabytes in my source code. And right now, I don't know how much process you will have in the future. How I make a decision how many memory size I should use for the process. So this is definitely not a good idea. So how your Linux kernel deal with this? It's assume, okay, I just don't want to do any limitation. You can use any memory you prefer. If in the system, if I have 4 gigabytes memory, you can use all of that. So, okay, I give you 4 gigabytes, I give you 4 gigabytes, I give you 4 gigabytes, I give you 4 gigabytes. I get every process 4 gigabytes. Okay, so in this case, problem solved, because every process can use the maximum, like a memory address, like a maximum space for the process itself, right? But here's bring another problem. Okay, if every process use 4 gigabytes, we have 5 processes. In total, there's 20 gigabytes. But we don't have a 20 gigabyte in the system, right? So how your kernel supports like 20 gigabyte to this process? Okay, so this is something we call virtual memory involved. We use our hard disk. The hard disk. Hard disk is much bigger. For example, one terabyte. Okay, we try to use hard disk, pretend the hard disk is a memory. So the user process won't know. User process think, okay, I use 4 gigabyte memory, but this 4 gigabyte memory is actually the virtual one. So it's a virtual memory. So for these 4 gigabytes, it's a virtual memory, virtual memory, virtual memory, virtual memory. So we try to provide virtual memory to these each process, but actually we try to separate into our hard disk. So this 4 gigabytes is for the process A. Process A. This 4 gigabytes is for process B, and so on. So we try to pretend we give you memory, but we give user. The kernel try to pretend I give you the memory, no matter how much you need, you can use the maximum number you want. If we have 4 gigabyte memory, you can use all of that. But actually, I try to store this memory, this data into another space in the hard disk. For the process itself, for the program itself, it won't know. It doesn't know what the memory address should be inside the hard disk. It's just know, okay, what the memory address in the memory, physical memory, should be. So each process know they can access to memory, but there's a virtual memory layer. They try to convert the physical memory, a virtual memory, to a physical memory number and put into hard disk. So this is the kind of the concept, how your kernel use virtual memory to manage the resource. Because memory is so short, only 4 gigabytes for everyone. And each process want to use all of them. Definitely it's not working. So you use another way to pretend they are use the actual memory, but no, they are not. They use the virtual memory. So this is kind of virtual. It's not in the physical memory, it's in hard disk. So when the kernel runs the memory, for example, the kernel right now, I want to run the A, it's trying to load the memory in the hard disk into the physical memory. So this is physical memory. It tries to load everything here into the memory and run it. This is the idea of virtual memory. Okay, the third abstraction is about files. So what are files? We say our kernel manages everything, every resource we have, right? So it's got every resource, including your screen, your keyboard, your mouse, your network, or your USB drive, this kind of stuff. So how is managed this? How your program access to it? So actually, kernel use a very, very small way. It try to package every single this part. It try to put directly the normal files, link, pipe, device, they are files. So actually, inside the Linux kernel, everything is file. Everything is file. File is file, directory is file, device is file, network socket is file. There's a pipe is file, link is file. So everything is file. So this is the last layer of abstraction is used. You try to package every device into a file. So if you want to access to these edges, this device, you can just tell kernel that, okay, I want to write message into this file. I want to write message into this socket file. So this is how your kernel manage the communication to make it simple. Don't need to like worry too much. Like, oh, if there's a device part, you should use different way to like to run it or work for it. No, in C languages, you see this device. Actually, they are files. So you can use the sense system code. We will cover what system code is. You can use the sense system code to like communicate to these files. So this is the last abstractions the kernel use. The kernel try to package every device, every component as a files, so it can like easily manage this stuff like in your user program. This is the last like abstractions. Okay, so we cover three abstractions. How your kernel, Linux kernel, manage the resource. They try to like package each running program as a process, and inside each running program they can use a lot of memory. But don't worry, because the operating systems use virtual memory to manage these physical, actually this memory stuff in each process. Then for each files, each device or network stuff, the kernel try to package them as a files. So for the user process, they can easily to manipulate or to communicate with each device by using file system code. So you can see here, kernel is kind of the god of your computer. It's trying to control everything. So all the resources there. Actually, the physical memory is controlled by the kernel, not your process. Your process actually is accessed to virtual memory, and the process itself is managed by the kernel. Kernel make you wrong, you wrong. Make you stop, you stop. And the kernel try to use context switch to like check, like to run each different process like at the same time by this switch stuff. So this is the idea how powerful your kernel is. But here's a question. I'm just a small programmer I'm writing a really small program, and I want to like use some network stuff, or I want to like ask our kernel to help me to like communicate with other process. Can I do that? Can I use this stuff? Of course you can, because when we write a program, we want to make it more useful. We definitely need to communicate with other device. For example, use printf, use scanf, right? You printf, you try to like show something to your screen, the message. So, which means you need the kernel to provide you a way to like show the message, right? But how to do it? Actually, how to do this? How your process talk to your kernel? Okay, so the idea of this is like a pray. So what's a pray? Actually, pray is a system code here. So this is your Linux kernel. Linux kernel is here. Everything want to talk to a kernel. If this is your application is your user program. Your user program on top of it, it can go through the system code. If you use system code, you can talk to a kernel. Of course, there's other library function. Use printf standard library. This library function also needs this system code to talk to a kernel. So actually, how to access to a kernel, how to like talk to, how to pray. God, please tell me to do this. How to do it? Actually, it's system code. So we will cover a lot of system code in the following like semesters. So you will see the system code for the files, the system code for network, the system code for process, and there's a lot of like system code you will see in this class from now. Okay. So, but the concept of the system code is that the system code is a way your user process can talk to the kernel without talking to a kernel, your process is useless because the process don't have permission to access to a device, don't have permission to talk to other program. Okay, so this is kind of the basic concept of your Linux kernel. Professor Joe, can you give us more detail about this abstraction, like how we use files, like how we use network, or how we create a process in our program, how we make our program more powerful? Oh, don't worry, don't worry. Okay, we will cover these materials in the following class. We will cover how you use system code, file system code to rewrite a file. And of course, because everything is a file, so you can use this file system code to communicate with your network. You can send message to other machine by using write system code, is a file IO system code. And of course, you can we will cover how you communicate to other process, like use pipe, use signal, or you can, or another one, like you might be used for the process is that you can create a process inside the program. So you can create your child process. One program can like give a birth to another program, maybe can give birth to multiple programs. We will cover these details in other video, in other lecture. So don't worry, this is just a summary of your Linux systems. There's so many details there, and we will cover each of the details, each of these abstractions in following lecture, okay? So I hope you get the sense, like what's the Linux kernel look like? Actually, Linux kernel is very, very strong, very powerful. It's trying to control everything. And especially it's try to manage your process in a multitasking way. So there's a schedule between the class, right? So there's a schedule between like the switch between each class. Okay, so there's three abstraction. One is process, the second one is virtual memory, so one is files. I hope you understand what's this means, what these three abstraction means, okay? So we will cover more details in other lectures, so don't worry. Okay, so hope you enjoyed today's videos. See you next time. Linux kernel is God.